Hello again. We are today going to look at synthesis and decomposition reactions. By this time, you've probably been introduced to a couple of other reaction types in class. This year, as I record, we've talked about double replacement reactions a fair bit, and we'll be starting single replacement reactions as well in large group next. But right now, we're going to talk about synthesis and decomposition reactions, which are two reaction types that are naturally able to be studied together because they're basically the reverse of each other. You'll see here in just a minute. Before we get into this, I want to remind you, or maybe for the first time, if you haven't seen it yet in your class this year, that there are 7 diatomic elements out there. These are called diatomic elements because when we find them as elements, and you see this underlined italicized here, when in the form of an element, and that's a really important detail, that they come in twos. So if we're breathing oxygen gas, we're not breathing oxygen atoms, O's, we're breathing oxygen molecules as O2s, you see here. When we breathe nitrogen, most of the air we breathe is nitrogen. Those are nitrogens that come in twos, N2s. So it's two N atoms that are basically triple bonded to each other that we're breathing, not single N atoms just floating around in the air. We don't see them like that. We see nitrogens as a molecule. We see oxygens double bonded to each other as a molecule when we breathe those in, not just individual oxygens, but paired oxygens. They do this, all 7 of them do this, to help each other achieve that noble gas configuration by sharing electrons and bonding. Once they get into a compound, they might get to a noble gas configuration by taking electrons from a metal or perhaps in bonding to a different element. But for a while, they can get along together okay, almost like roommates, helping each other survive until they find someone else to bond with in an ionic compound, for example. So when you see these elements as elements, they come in twos, not individuals, but come in twos. Not all elements do this. In fact, we're going to say that the other elements, of which there are over 100, come individually as single atoms. So if I'm breathing helium gas, I'm breathing helium atoms. If I'm working with iron, I'm working with iron atoms. So just these 7, you'll see them show up in more and more equations as we go through the year, but just kind of let you know, these 7 come in twos. Watch for them in all reactions, not just synthesis and decomposition, which is the focus of this video. So a synthesis reaction, you've already actually seen a little bit of, at least this year you have. I want to remind you where, in case you are in my class this year, we worked on this. This is that POGL activity where we introduced the different reaction types kind of as a review of 9th grade, and you sorted out these reactions. You'll see a lot of equations on here, but they're grouped already. Synthesis reactions, which I said here, is basically taking 2 or more simple substances and combining them into one more complex one. We see that here in set A. Each of these reactions in set A shows 2 simple things, like iron and oxygen, becoming one more complicated thing, iron oxide. Nitrogen and hydrogen becoming NH3, which is ammonia. SO2 and O2 become SO3, which is a little bit more complicated than SO2, and so forth down the list. So there's simple things becoming more complicated things. That's a synthesis reaction. And you see in a lot of these equations, there are some of those diatomic elements that I was talking about, like O2 and N2 and H2. They're all over on this sheet. There are others as well. Okay. So a synthesis reaction is simply taking 2 things and putting them together into one. It could be more than 2 things. Occasionally we'll see 3 or maybe even 4 things merging into one, but typically it's just 2, maybe 3 things that combine to make one larger, more complex substance, a synthesis reaction. So here A plus B makes some new AB. We don't say A plus B makes C because then we kind of lose track of the A's and the B's. They're still there. The same atoms are still there. We don't take carbon and oxygen, put them together and make, say, sulfur or something. Carbon and oxygen are going to combine into something that still has those 2 elements, like carbon dioxide or carbon monoxide. Now, a decomposition reaction is just the opposite. And that's why we kind of put these together. Decomposition is something decomposing. And when we think about decomposing like a piece of roadkill on the side of the highway or something, eventually it decomposes, it rots and turns into gases that stink and so forth, and eventually kind of goes away. Or if you find a dead bird laying in your yard, if you just leave it there for a year, I don't know why you would do that, but if you left it there for a year, it would just kind of gradually decay. The tissues would break down, it'd turn into gases, and it kind of just goes away, most of it. Okay? Decomposing, taking something complicated, breaking it into 2 or more simpler things. So decomposition reactions look like this. CD becomes some C plus some D. Okay? So again, the 2 elements that were together, maybe more than 2 elements, are breaking apart somehow, okay, into something simpler. Now, let's look at the examples here. In set B on this assignment, you see compounds like magnesium carbonate breaking down into magnesium oxide and carbon dioxide. Each of those is only 2 elements, so we would say that those are simpler than the original MgCO3, which is actually 3 elements. Water here can break down to perform or form hydrogen gas and oxygen gas. So water, which is pretty simple in and of itself, becomes even simpler as two elements. Down at the bottom, ammonium carbonate breaking into three things that are each simpler than the original. So as we look at decomposition reactions, they're going to be one thing on the left becoming two or more things on the right, as you see here. Now, what you've got here is a table that I want you to put into your notes. So if you're taking down some notes, make yourself a little table like this one. It's going to have a label across the top that says synthesis reaction. And as you read this chart from left to right, okay, you're going to be seeing that the things on the left are going to combine through a synthesis reaction to form the things on the right. And if you read them in reverse, as you see down here at the bottom, decomposition reactions are labeled. That's because if we take things and read this table, this sort of a table in reverse from right to left, okay, you're going to see the thing on the right, the one thing over here in this box on the right, is decomposing to form the more than one or two things over here on the left. So two things becoming one thing, that's decomposition. One thing becoming two things, that's decomposition. Two smaller things becoming one thing, that's synthesis. So we're going to have four different sort of categories or templates here that we're going to fill into the rows on this table. So make yourself one like this or add to it as we go. And if I go by, go by one too quickly, feel free to pause and write in what I've got here into your table and then listen to kind of the explanations. Or at the very end when the table's complete, feel free to pause and jot the whole thing down at that time if you wish, and that way you don't have to try to keep up. Down here at the bottom, you see I've got two notes. X in this table will represent any metal. You're going to see X show up a number of times. And A will represent any non-metal. So an X could be a metal from the left side of the periodic table, lithium or iron or copper, lots of things. The A that you'll see in these equations represents any non-metal. And I dare say it's any non-metal other than oxygen, because you'll see oxygen actually shows up in here a whole bunch just by itself. So a non-metal like sulfur or nitrogen or carbon or chlorine, one of the non-metals that bonds and forms compounds. All right, so let's fill this in. The first reaction type of synthesis and decomposition, if I'm reading this from left to right, a metal and a non-metal are going to join together to make some binary compound, a binary salt. A metal, X, some metal, plus some non-metal, A, gives me some binary salt, which we'll call just generically here XA. Now, we don't know what the formulas are, so we can't say if it's XA2 or X2A or XA3 or X2O5, X2A5. It could be any combination of those with subscripts. But the format is that. Metal plus non-metal makes some salt where the metal will be first and the non-metal will be second. So a metal and non-metal make a binary salt. That's the simplest one. A metal oxide. Oxygen loves to bond with everything. So you'll find oxygen bonding with any other element on the periodic table that forms bonds. So metal oxides would be any metal with oxygen. Could be like calcium oxide. Could be like iron oxide. Non-metal oxides, AO here, is a non-metal with oxygen. We've seen lots of these already. Carbon dioxide is a non-metal carbon oxide. Sulfur trioxide. There's all kinds of them. And so as you look at these equations, we're going to look for a metal with oxygen and a non-metal with oxygen. And then we're going to join those together into one even bigger thing. And we're going to call it a ternary salt. So here the equation says metal oxide and non-metal oxide joining together into some ternary salt. If we read it in reverse, the ternary salt can break apart back into those things. What I want to draw your attention to is down here in the equation as well. XO, metal oxide, AO, non-metal oxide, makes a ternary salt, which has the formula and the arrangement XAO, the metal, the non-metal, and the oxygen. Okay. We're going to see that in the examples that we'll go through, that XAO helps us get the elements in the right order. And then what's left for us to do is to figure out how many X's, how many A's, how many O's you're going to need to make a compound that actually works. Something that we can give a name to is the goal. Oops. The third category of compounds in our little table here is a metal oxide combining with water to make what we call a base. Now you're going to recognize it as a hydroxide compound, something that ends in that OH ion that we've started to call hydroxide more and more and more. This is the sign of a base. So as opposed to an acid, when we see an OH on the end of a compound, it almost always means we're working with a base in terms of acid-base chemistry. So an easy way to make a base then is to take a metal oxide, add water to it, and as that happens, the compound will produce a base, a metal hydroxide. XOH. So in the equation that you'll see here, the X again could be any metal, and we're going to make some kind of hydroxide compound. Sodium hydroxide, barium hydroxide, where the X will be whatever metal is appropriate to the question. It could really be any metal at all. So you could call it a base, which it is. You could call it a hydroxide, which it is. Depending on where we're using it, you might find each term is more fitting. And our last row here is the opposite of a base. So we're going to make, how do we make an acid? Well, it's kind of the opposite. So bases and acids are opposites. And the way we make them is kind of opposite. Now, both of them use water. In fact, in most chemistry definitions, acids and bases are both kind of acting in solution in water. So the water is almost sort of necessary. But they actually react with the water to make the base when we use a non-metal like we see here. So a non-metal oxide combining with water will give us some kind of an acid. And a non-metal oxide has a general formula of A for our non-metal, O, so AO, plus water makes HAO. And again, notice we put them in a very particular order. H for the hydrogen, every acid that we'll work with in first year chemistry, I should say almost all of them, will start with H, because it's just kind of the sort of first element that's typical of simple acids that we look at in first year chemistry. A for our non-metal, and then O for our oxygen. A lot of acids that follow this format, HAO. There are lots of acids that don't. Okay, I'm here to tell you, there are lots of acids that don't look like HAO. They're more complex than that, or even less complex than that. But the ones we're going to be looking at, probably identifying here, will be those where HAO is going to come about by the combination that you sort of see here. So again, remember, these can be read from left to right. They can be read from right to left, and they work the same either way. We're going to get the same result, essentially, through the same arrows here. It's just that when we read these forward, it's a synthesis reaction. It's two things become one. And as we read them in reverse, it's a decomposition reaction where one thing breaks down to become two. All right, let's look at some examples. You should have this assignment. You should have gotten it from me. If you didn't, you can just write these examples down into your notes and add them to the assignment later on. Stop and see me or the other chemistry teacher just as soon as you can to pick up a copy of this. Okay, so this is for synthesis and decomposition. We're going over it in small group in class, but if you've missed for something, you might need to come and get a copy of the sheet if you didn't get it beforehand. So this will be synthesis and decomposition practice. So this should be one you find on there. Zirconium plus fluorine makes what? So again, the guide to this is going to be use that table you just wrote out. Use that table that you drew and figure out which line of the table we're using kind of by the ingredients that we're given. So zirconium and fluorine. Well, go to my periodic table. If you need to look at it, do it. Here's my periodic table. Zirconium, the metal, way over here on the left side. Fluorine, we know, is kind of the king of the nonmetals over here in the top right corner. So we have zirconium and fluorine, a metal and a nonmetal. Hopefully you recognize then that according to our table, a metal zirconium and a nonmetal fluorine will combine to make a binary salt, which is going to have the format of zirconium and then fluorine, okay, put together. Now, that's not the whole story, right? We still need to write a formula. So give me a moment here. I'm going to put my pen on the screen, and we'll fill this one out together. Let's go with red. All right, so zirconium and fluorine, put them over here. Zirconium and fluorine, X, then A, and then give them their charges in order to figure out how they're going to combine to make a salt. Okay, so fluorine in compounds is always -1. And zirconium has a charge of, maybe I don't know. I do, but maybe you don't know. So let's take a look. Back to our periodic table. Here's zirconium way over here. And the only oxidation number we see for zirconium is right here. It's a 4+. So my zirconium needs to be 4+. If that's the case, then zirconium's 4+ will need 4 fluorines, each of them -1, to make this a neutral compound. So we would call that zirconium fluoride. Now, I'm not asking you for names here. If I don't give you words, you don't need to give me words, but you should be able to name any of these. Notice we've also got fluorine gas here as a diatomic element. That was from our original list, those 7 elements that tend to form diatomic elements. And then zirconium here is by itself, plain old metal. I want to point out one last thing that will go on, and that is that zirconium, when it's not yet in a compound, hasn't lost or gained any electrons. It doesn't have a formal oxidation number or charge. And so zirconium's official charge over here would actually be 0. A lot of folks bring this 4+ from zirconium off the periodic table, and everywhere they see it, they're going to put a 4+ down. That's only the charge on zirconium when it's in a compound and has lost those 4 electrons that we would take to achieve this charge. The same is true of fluorine. Fluorine in a compound will always be -1, But before it's in a compound, if it's just plain old diatomic fluorine gas, its charge is 0. Fluorine gets a 0 charge. So these don't take on the 4 and 1 that you see on the periodic table until they're in a compound. And that's really important as we go on throughout the year to remember. Okay? So let's look at another one. This is number 5, calcium oxide plus water. All right, calcium oxide plus water. Hopefully you look at this and recognize we're talking about a metal oxide reacting with water. This was the third row of the table that I went through with you earlier. So we have a metal oxide. Calcium is my metal. We don't often think about calcium as a metal if we haven't done chemistry, because calcium's like, oh, that's in my bones. I don't have metal in my bones. You do, especially if you've broken it and they've put a plate in there or something. But calcium is a metal. It's in your bones. Magnesium is a metal. It's in your bones. Blood's being made in your long bones, in your marrow, and blood's got iron in it. So there's even some iron in your bones in there if you talk about the right ones. So as we look at this equation, calcium oxide going together with water, we are talking about a metal oxide. Calcium is my metal here. So think about tracking through there, that's my metal. So as far as finishing this out, we're going to get a base. We're going to get a hydroxide compound. It's going to have the metal X, which here is my calcium. And then it's going to have this hydroxide ion. And don't forget, hydroxide is OH with a -1 charge. That's on your ion list that we've been using a lot of already. So instead of just saying XOH, I can say calcium along with the OH group. And the reason that's nice and helpful then is because it'll help me write the formula correctly right away. All right, how do we do that? When we're working with these elements like calcium oxide, they already have charges of their own. They're in compounds, so calcium's a +2 and oxygen's a -2. Water, hydrogen's always a 1 and oxygen's a -2. So these oxidation numbers, which is really the better term, not charges so much, but we'll use either one for now. The oxidation numbers on these calcium and oxygen and hydrogen and oxygen atoms, those are still the same charges we're going to use over here to finish writing out the formula. If they have a charge already, you should use it again for most every synthesis and decomposition reaction. But we also know that this OH group, hydroxide, from down here, has a -1 charge. So I'm going to go ahead and say that hydroxide is -1. I do know that calcium is +2. I'm going to go ahead and call that by +2. And if I think about how I've written formulas and practiced that, a calcium with a +2 charge will need an hydroxide ion. It'll need 2 of them, like so. And now we're done. So calcium oxide becomes calcium hydroxide when water is added to it. Synthesis reaction. 2 things, rather simple, becoming 1 thing, slightly more complex. Carbon dioxide and water. This is number 2. Carbon dioxide and water. Now this is a word equation, so we want to work with the words, but we also want to work with the equation. So to kind of help us with that, if you can't recognize right away that this is a non-metal oxide with water, then write the equation out with the formulas too. So carbon dioxide, CO2. That's one we know from our childhood. Right? And water, H2O. Becoming what? So we've kind of got a word equation that we want to finish, and then we've got an actual chemical equation that we want to finish. So to do that, we're going to look down here again, non-metal. A is my non-metal here. Well, that's carbon. Non-metal carbon oxide, and then of course we have our water, is going to give me an acid in this format, HAO. Well, again, it's not A now because I know it's carbon, but it's going to be in that order, HCO. Now, I spread them out a little bit so I can add some numbers in there. But what I want to do to figure out the numbers that are in there is use the charges from the other side again. So on the last one, we figured out calcium was +2, and we used that +2. We want to do the same thing here. We want to figure out what the charges are on the oxidation numbers, are on every element in the compounds that we've got. So CO2, oxygen, always a -2. Carbon then must be +4 as far as an oxidation number goes. 2 oxygens that are -2 means we have to have a +4 carbon to keep things equal and opposite within that compound. And in water, we're going to see that one a lot, always +1, -2. Now I'm going to bring those charges across to the other side and say hydrogen, you're still a 1+. Carbon, you're still a 4+. Oxygen, you're still a 2-. All right, and now we're going to put these together to make a compound because this is the order, HAO. But it isn't a quantity. It's not telling me how many hydrogens, how many carbons, how many oxygens. It's just telling me the order of things. And we want to bring the charges across from the other side to help us make that out. So to write the formula, we need to look at these charges and decide how we're going to make this compound work out, because whatever comes of this, it needs to be 2 things. Okay? HCO isn't quite right, but when we get to our compound by the end, it should be two things. It should be neutral. In other words, it should have as much positive as it has negative, and it should be nameable. By the naming rules and stuff that we've talked about, we should be able to give this fella a name, okay, and call it by something appropriate. I can't name HCO because I don't have an idea what to call CO as far as an ion that we've worked with up to this point. But by the time we get done, you should be able to. So, how do I know this isn't done? Well, I can't name it, for one, but it's also not neutral because 1 plus on my hydrogen and 4 plus on my carbon together make 5 plus. And over here I have 2 minus. So 5 plus and 2 minus, that's not equal and opposite. That's not neutral. How to do it? Well, you might recognize that with 5 plus and 2 minus, it's going to be difficult to do that because 5 plus is an odd number and 2 minus is an even number. And those just don't go very well together. So what we want to do is kind of think about how we can get the odd one to be an even one. That's a helpful way to approach this. There's more than one way to do this for sure, and I'll show you another one here in a moment. But I'll think that, with 4 and 1, that makes 5. That's odd. If I went 4 and 2, because let's say there were 2 hydrogens here, then that would be 4 from my carbon, that's 4 plus. And that would be 2 times 1 from my hydrogens, that's 2 plus. So far with it as written here, I have a total of 6 plus from my hydrogens and my carbon. And that means I need to have 6 minus over here because this compound needs to be neutral. All right, how many oxygens will it take down here? Okay, how many oxygens will it take in order to get this compound to be neutral? Well, if each oxygen is worth -2, I'm going to need 3 oxygens times -2, give me -6. And this adds up to 0. And compound should be neutral. We've achieved that. We have +6 and -6. And it should be nameable. And we can name this. All right, I've kind of made a mess of my space to write the name in here, but we can still name this because I know my naming rules. And if I go look up the ion, we've got CO3 is known as carbonate. And we know our naming rules say that any acid ion ending in ate means I have to end in ic. So ates become ic. Carbonic acid. Right, so 8 becomes ic, and then we throw the name acid on the end. This is carbonic acid. Carbonic acid, super important acid in maintaining your blood pH. And it's also in soda. So there you go. So carbonic acid. That's what we've made. Now there's another way to think about kind of approaching how would I figure this out? Because you remember what we did? I just kind of put a 2 on the hydrogen to make it even. It's almost kind of like I'm guessing at it. If you're not quite comfortable with that, think back a step to when we had HCO here. 1 plus, 4 plus, 2 minus. Now I need to know how to put these together. If it's going to be an acid and we're going to be able to name it, then we're going to need an ion that contains both carbon and oxygen. Right? There's going to have to be something that contains just those two because hydrogen, the acid here, part of it, the acid ion at the beginning, is paired up with some anion, some negative part that has carbon and oxygen in it. And if you go looking at your list of possible ions, the only ones you're going to find that include carbon and oxygen are going to be carbonate, which is what we decided it is, and the other ion was oxalate, which is C2O4. Now, how the heck do I decide between these two if I know those are my two choices because they contain carbon and oxygen and nothing else? How do I decide between these two? And the way you decide then is to look at these more closely and actually decide within the carbonate ion, what is carbon's oxidation number? And you'd figure out that it's +4. Okay, so if you can think about the ions in terms of their oxidation numbers, you'll be able to figure out that the carbon has a +4 ion oxidation number in carbonate. This would be a 4 plus carbon, and this would be a 2 minus oxygen. And when I put those together, I get a -2 overall charge. Down here on the flip side, oxygen has a -2 oxidation number. And the way we look at carbon here, it actually has an average oxidation number of 3 plus. And we can't use that because we know carbon had a +4 oxidation number when this thing starts. Way over here it's CO2. So this doesn't work because the carbon has the wrong charge. And up here, this works because carbon has the correct charge. So you could use the CO3 ion and make your compound from there. So if you have questions about how to figure out those oxidation numbers, see me in class. I'm not gonna add to that just now, but I can certainly explain it to you in person. Okay. So we finished this one. Sorry, I got to slide the text there. Let's look at number 4. It'll be our last example. The manganese 2 oxide. plus sulfur trioxide. Now we've got here the fourth and final option from our table. It's actually the second one on the list. And that is when a metal oxide, like manganese 2 oxide, joins with a non-metal oxide, like sulfur trioxide, to give me a ternary salt. Now I've kind of put the non-metal component here in green, so we can kind of see it, trace it through. The non-metal A is found over here in the ternary salt. That's still going to be my sulfur in some way. Okay, so to do this, we're going to take our metal oxide, our non-metal oxide, and combine them, not just mashing them together, but in this form, X, then A, then O, metal, then non-metal, then oxygen. So let's start up here. Manganese 2 means manganese has a +2 charge. Oxygen, always a -2 charge. So Mn 2 plus, oxygen 2 minus, that means MnO works, right? Just MnO. That's neutral. Sulfur trioxide, now we got a Greek. So sulfur trioxide means sulfur with 3 oxygens. And then on the other side, we're going to put those together in the order we've got, XaO. So metal is my manganese, A is my sulfur, my non-metal, and then oxygen. Now notice what I didn't do is bring along any numbers from over here. I don't bring this 3 from the SO3 or anything like that, but what I do want to carry along are the charges. So manganese is a 2 plus. We're going to reuse that over here. So whatever the heck we make is going to have manganese 2 in it as well. The oxygen is still -2, so I'm going to bring that along. The real question here is then what is the sulfur's oxidation number at the beginning? Now remember, this guy is a neutral compound, so it has to add up to 0. So as I'm figuring out what sulfur's oxidation number is, I'm going to base it on the fact that oxygen has a -2 oxidation number. 3 times -2 makes a total charge on the oxygen side of things of -6. That means I need to have an equal and opposite +6 to make this compound neutral. And being that there's only one sulfur atom in the compound, the whole +6 needs to come from that one sulfur. So sulfur's oxidation number is +6, oxygen's is -2, and that gives us a neutral compound. But the important part of that little bit there is that this 6 plus on sulfur is going to still be 6 plus over here. And that helps me get to the end of my story because, look, 2 plus and 6 plus mean that's a total of 8 plus. I've only got one -2 oxygen here. So it's going to take 4 oxygens, each of them worth -2 to make -8. And that's equal and opposite to the total of +8 that I get from the manganese and the sulfur, just one of each. The other thing is, can we name it? Should be neutral, should be nameable. It is neutral, but is it also nameable? Absolutely, because we know manganese still has its oxidation number of 2, so it's still manganese 2. Okay. And then the SO4 I can look up, and I've used a lot. I know SO4 is sulfate. Manganese 2, sulfate. And that's the compound that would be made, our ternary salt. A salt, it's ionic, containing 3 elements. That makes it ternary. Okay, so those are examples of the different reaction types, and we do keep those charges all the way through. Okay, as I mentioned, the sulfur charge comes through, the manganese charge comes through, the oxygen charge comes through. The only place, okay, and we'll be done, the only place where we don't bring the charges through are here at the beginning with our zirconium and our fluorine, because they didn't have a charge yet. They were still solo elements that don't have a charge until they've joined with somebody. And now at the end, they found each other and they've taken on a charge as a result. Okay. So those are our 4 types of synthesis and decomposition reactions, all shown to you here as synthesis only. The video won't go into the decomposition, it's getting a little too long, but I'll post one as soon as I get a chance to make you one about a decomposition example for each of these as well. And you'll have one going the other way. For now, perhaps emphasize the synthesis work, and then when you feel comfortable with that, try to take one of those decomposition reactions and flip it. Think about it in reverse and see if you can't use it the other way around, taking the thing on the right side of this table and making it into something on the left, the 2 things on the left. Until then, good luck. Don't be afraid to make mistakes. We learn best from mistakes, not fear. Dive in, try some, bring your work to class, and we'll see how you did. See you then.